2014 locals. We have 41 through 50 today. And let's get started. So 41, this is a Voltaic cell. So in case you're not like up to speed on terminology, Voltaic or galvanic cells, the reaction that's happening is spontaneous. It's what's providing the power. In electrolytic cells. It needs power to be run, so it will be hooked up to a battery. So the cell potential is that, and we have standard conditions and standard molarities. What increases the voltage? So we need to know what the Nernst equation looks like. This should have a knot. So this is called the Nernst equation. Basically, this E talks about standard conditions, so we call that E naught. And then this is 8.3145. It's the energy R. It's not the gas R. And then T describes temperature in kelvins. N is how many moles of like substance you have. And then F is Faraday's constant. I think for USNCO they want you to do 96,500. More accurately, it's like 96,485. And that would be coulombs per mole of electrons. So now that we got like the basics out of the way, we can start like utilizing this. So the only way that we're going to make E greater than E naught, because we want to increase the voltage, we have to make Q less than 1. Because if we make Q less than 1, then ln of Q is going to be negative. Then we have this negative sign here, so a negative times a negative, that kind of looks like equals. But anyways, a negative times a negative is going to make a positive, so you're going to add some number onto E naught, which is going to make E bigger than E naught. So you want to decrease Q. And I mean, just from like prior knowledge, you should probably know that the reduction of lead is more favorable than the reduction of nickel. When I say lead and nickel, I mean the 2+ ion solutions. So if we take that into account, we know that lead is being reduced, nickel is being oxidized. Then we can write it like this. I'm just omitting states for now because it's a little bit easier to do it that way. So if we dilute Ni2+, we're decreasing Q because we're making the concentration of a reactant smaller. So that decreases Q, makes E greater than E naught. I'll just go through the other choices for, thoroughness. Larger Ni electrode is used. We don't see anything about the size of the electrodes in the Nernst equation, so get rid of that. NaCl is added to precipitate PbCl2. That would actually have the opposite effect because we're lowering the lead ion concentration, and that would be lowering a reactant concentration instead of a product concentration, so that would make our Q go up, and that would make E less than E naught. So not what we want to do, the opposite of what we want to do. Okay, so quick lesson. If you add something of a certain concentration to another solution of the same concentration, you're not changing the concentration. So that's why D is not right. Alright, so for 42, aluminum is produced by the electrolysis of aluminum oxide. How many hours does it take to make that much? Okay, I don't know the molar mass of aluminum off the top of my head, so we can take a look. 2698. Okay, so 250 grams of aluminum is equal to 250 over 2698, which is 9.266 moles of aluminum. And how many hours? Okay. So we know that aluminum has a +3 charge in Al2O3. So if we multiply this by 3, which is the ratio of moles of electrons to moles of aluminum, then we get 27.2 0.798 moles of electrons involved. And then we basically multiply by Faraday's constant to find out how many coulombs this takes. So, or sorry, not multiply. We need to, oh yeah, multiply. I don't know what I'm saying. I just use this number because it gets pretty much the same result and I'm just more used to using it. So if you do this, coulombs over moles of electrons, then you would get a big number. I'm just going to say 2.68 times 10 to the 6th coulombs. That's how much current you would need to provide. You have 5 amp. Oh, okay. I'm not an electricity person. I don't know what like the terms for these are, but you need that many units of charge, which coulombs describes. 5 amperes means you provide a current of 5 coulombs per second. So 5 coulombs per second, if we divide this by 5, we get that we need 5.36 times 10 to the 5th seconds in order to transfer that much charge. So I think we all know how to convert to hours. We just divide by 3600 and that gets us 149 hours. So that's why we choose B. Sulfur atom in its ground state, blah blah blah. How many orbitals are occupied by at least one electron? Okay, so 3p4. I'm going to solve this up here. So it said 1s2, 2s2, 2p6, 3s2, 3p4. Let me just add up to make sure that I didn't get that wrong. 12, 16, 16. Okay. So here we're trying to figure out how many orbitals are occupied by at least one electron. So this is one orbital, this is one orbital, this is 3 orbitals, this is 1 orbital, this is 3 orbitals. So 1 plus 1 plus 3 plus 1 plus 3. Because here we need to realize that anytime we're talking about a p subshell, there's 3 different p orbitals. There's px, py, pz. And you can hold 6 electrons total, right? Because 2 per orbital. If we have a 3p4 situation, what that means is that we put 1 electron into each of the p orbitals first. So we have 3 electrons in different orbitals, and then we rotate back, and then we add a second electron into one of the orbitals. So still we're only filling 3 of those orbitals. So 5 plus 4 is 9. Yeah, so that's why we choose D. 44. Which of the following transitions would a hydrogen atom absorb? Okay, so there's almost always a question like this. Like it gives energy levels as answer choices, and then it poses some kind of photon question, like emit or absorb a photon. The first thing you have to do is look at whether the transition is from a higher energy. I just combined 2 words. Okay, from a higher energy level to a lower energy level, or vice versa. From here, we need to absorb a photon. So you need to go up in energy level, because if you absorb a photon, you're gaining energy. So 1 to 2 goes up, 5 to 6 goes up, 3 to 2 does not go up, 7 to 6 does not go up. So you can automatically eliminate B and D. So longest wavelength, that means you want to have, well, a long wavelength correlates with a lower frequency, which correlates with a lower energy. So that means you want the lowest energy gap between the 2 states. And if you think about, like, I can't draw, but if you think about, like, energy diagrams, like, if this is n equals 1, this is n equals 2, as you get up, like, the energy states are closer and closer and closer. Like, you can see there this huge jump here. There's kind of a medium jump, and then small, really small jump. So that means 5 and 6, n equals 5 and n equals 6 are going to be a lot closer in energy to each other than n equals 1 and 2. So you want the closer in energy states because you want long wavelength, aka low energy photon. So that's why you choose C instead of A. Okay, which of these is not possible? We can probably work backwards. So all of these electron spins are possible because you can only have plus minus 1/2. Oh, okay, never mind. If we work forwards, we go faster because you can have any n, right? Like as long as it's not outrageously big. These n's are all fine. but you can only have an L that's equal to n minus 1, any integer in between 0 and n minus 1 inclusive. But obviously 4 is not 4 minus 1, so we choose C. 46. What property of the oxygen atom is represented by that? I mean, this is really just knowing your periodicity stuff. I mean, it's not even memorization, it's just like knowing what it means. So adding electron to gaseous state atom, that's electron affinity. Taking one away is ionization energy. Electronegativity just talks about like how much a certain atom will attract electrons, or like be more susceptible to having those electrons closer to them. And then lattice energy is just like you have this like solid usually, and it's like how much energy does it take to break it, which usually you can find out using like Born-Haber cycle if you're really into that, or you know, just comparing ionic radii and charges using Coulomb's law. 47, isoelectronic species has the largest radius, so it already tells us they're all isoelectronic, so we don't need to do any investigation on our own. Basically, if they all have the same number of electrons, the one with the largest radius is going to be the one with the lowest effective nuclear charge, because the higher your effective nuclear charge, the more the electrons are going to be pulled in to the nucleus, and the smaller your radius is going to be. So here, I think P is 15, S is 16, 17, 18, I think K is 19, and Ca is 20. These numbers are their atomic numbers, which correlates with effective nuclear charge, and P has the lowest, so that's why you choose C. Non-metallic to metallic with increasing atomic number. Okay, haven't seen a question like that before. But obviously we know this is going to happen on the right side of the table, because you're not going to transition unless you pass the metalloid strip, like that diagonal strip with the metalloids. So not you, not you. I really want to say not you because we all know these are halogens and they're non-metals, so I'll just say it. It does happen on the right though. And B would work because N and P are just like poster child non-metals. Arsenic is a metalloid, and I think antimony is either a metal or a metalloid. I don't think you really have to know what it is, just because it doesn't appear in questions at all, but yeah, it's a metalloid. Where were we? 49. Which atom is least likely to violate the octet rule? Okay, if we just look at these, H, it almost always violates the octet rule because you have a 1s orbital and you only need 2 electrons to fill it up. So octet means 8, 2 is not 8. Hopefully you can see that too. Cl. Let's take a look. Cl can violate it if it wants to because it's in the 3rd period, so it can start doing expanded octets and going past 8. But I mean, yeah, so it can be. If you've heard anything about boron, it's basically like you can have a bunch of hypovalent, I think that's the correct word, you can have a bunch of hypovalent compounds because boron, it's pretty much happy to just have 3 electrons with it. Yeah, so that's why I choose F. In the Lewis structure for formic acid, that thing, how many bonding pairs and how many lone pairs of electrons are present? So if we just visualize this, we know that this is a carboxylic acid, so we have that C double bondo, single bondo, H. So on the double bondo, there's going to be 2 lone pairs. On the single bond O, there's going to be 2 lone pairs as well, so we already have 4 lone pairs there, and nothing else is going to have lone pairs. So the only choice here with 4 lone pairs is D. Alright, so that wraps it up for this video, and we'll see if I make one for the next one, depending on how learnable the orgo is without straight memorization. Alright.